Okay, good evening, everyone. So today we are going to start on new module, and that has to do arithmetic in digital logic. So in some ways, we have seen at least a little bit of arithmetic, but only in context of positive numbers. And last time around, we saw like how we can do max and things like that, but this module will probably spill into next week. We're going to look at how numbers are represented um, in in terms of bits, and including going beyond simply positive integers, and also how we do arithmetic with it. So, yeah, in just a sec. Yeah. So, in terms of uh, one of the takeaways from what we have seen previously earlier in the course is that we can use the same bits, kind of like, let's say I give you a vector of 8 bits or 16 bits. We can use it to represent whatever information we want, right? I mean, that design is up to us. uh, Early on in the course, we saw how we could use it to represent playing cards and dates, and in the homework we saw how they're used for genetic material and colors. And of course, we have often referred to these n-bit numbers in terms of their standard binary base 2 numbers also, right? So the bit vector naturally maps to a base 2 number. um, so uh, so we are going to build upon that and kind of look at how various different kinds of numerical entities can be represented in bits. Okay, so let's start discussing that. So how do we represent numbers with bits? So um, so it's pretty straightforward to represent non-negative numbers. And essentially, we take the analogy from our usual base 10, and to each bit in a vector of bits, we assign some weight to it, right? So in base 10, our weights go as 1 for the unit digit, and then 10 and 100, and so on and so forth. In base 2, in base 2 it becomes 1 and 2 to the power 1 and 2 to the power 2, and so on and so forth. So if you think of a vector of bits to be to have the bits numbered 0, 1, 2, 3, like that, and typically we write them so that bit number 0 is at the rightmost point, and kind of then as we move from right to left, the index the index of the bit, or the position number of the bit, goes up. So, and we assign, just as I described a little bit ago, kind of the weight to these positions. So 2 to the power position number. So if position number 0, then it's weight 1. If position number 3, weight is 8. And basically, this is how uh, sort of numbers have been represented historically. And in this case, since we have only two possible symbols, 0 and 1, so base 2 is kind of a natural thing. So for example, if we have this number 11001, then we'll basically kind of add up the base contributions, right? So wherever we have a 1, we get the corresponding base value. So for example, uh, uh, at this point we have a 16 because we have a 1 as the base value, and 2 to the power 4 was of 8. Okay, and then we add them up to get the number 25. Okay, now later on today we will see how we can generalize this concept to represent signed numbers, to represent real numbers, and things like that. Okay, but for now we know how to represent positive numbers, so 0, 1, 2, 3, and so on and so forth. Now, what one has to remember is that when you store bits in computer memory, then bits are just bits. It's like inherently they don't have any meaning. It's not like just because at a memory address we are storing this bit 11001 that it implies 25. It's only when we say, hey, this is, I'm going to interpret it as a base 2 number, that's when we say, okay, oh, it is 25. But it could also be, I don't know, like the identity of an object in a room, or anything, right? I mean, I can use these bits to represent anything. So all we know is that if I have n bits, then I can represent 2 to the power n different things. And how we code the stuff we want to code, which could be numbers, but could be anything else, playing cards, dates, depends upon some strategy of coding that we agree upon. Now, if you go back, recall our module number 2, when we had talked about that there is no one right representation. So do you recall what were the factors when we, what were the factors that one would consider in picking a representation?
Like how much, like the amount of memory you would need, or like
Okay.
how easy it would be to switch from one state to another?
Exactly. So amount of memory, what's one? How easy would it be to do certain operations on it, right? So remember, for calendar, we had talked about different schemes had different difficulty in things like, oh, what is the next date, right? I mean, so we always, if you're trying to represent information, then of course we have in mind that we're going to do some processing on it. And some presentations are going to be easy in doing the kind of operations like what's the next date, and some are going to be hard. In the homework you saw, like we wanted to find which months have 31 days. The representation we had, which was basically as a binary number, as a base 2 number corresponding to the conventional month number, it wasn't that kind of straightforward. We needed some circuit. But on the other hand, you might imagine some alternate way of representing months, where maybe we have a bit indicating, hey, this month has 31 days versus 30 days versus 28 days or 29 days, right? So in that representation, it would have been easy to figure out whether the month had 31 days. So interpretation, so how we represent is really depends upon what we want to do with it also. So so for example, let's say I have 32 bits and I want to represent integers. Then there could be many different strategies. The strategy I described out here is just one of them, right? There could possibly be other ways of representing numbers in those 32 bits, including one-hot coding, which would be very inefficient because I can only represent 32 numbers in it. And, you know, for all we care, we might have said that, you know, I'm going to do all of this and going to invert the digits. Okay, so like, for example, the number 0 would be represented by 1, 1, 1, 1, 1. Number 1 would be represented by 1, 1, 1, 1, 0, and so on and so forth. I could make up my own coding. There is nothing. Now, this representation that we picked, that we use, is common, like we are all used to it because of analogy with base 10, and also mentally we have learned how to do operations like addition and subtraction and all, right? Carry in, or you sort of carry forward from right to left, or borrow from left to right. Those kind of operations we learn in elementary school. So conceptually we find it easier to, that if you were to ask what's the most natural way we will think to represent positive integers, then this is what will come to mind. But I could use the same 32 bits to also represent other things, right? I could say, you know, I want to represent positive and negative numbers. So maybe I can use some strategy where I can have half of these numbers be positive and half of them be negative, or well, not quite half, because we have even number of things possible in 2 to the power 32, and we do want to represent 0. So then we are left with odd. So maybe I can have some k negative numbers and maybe k plus 1 positive numbers. I can use the same thing to represent real numbers, right? What are the different ways we write real numbers in our standard arithmetic? Anyone? Like
decimals,
just
roots, fractions.
Fractions, okay.
Scientific notation.
Okay, scientific notation. So with the e, right, or kind of 10 to the power something. And then straight with a decimal point, right? Like 2.3 or stuff like that, right? And when we write it as like 2.3, then the weight for 3 is what, 1 over 10, right? So the weights go to the right of the decimal point in increasing power of 1 over 10. So these are some of the common ways, indeed. Thing to remember is that the underlying logic doesn't know what a bit represents. It's really up to us, right? So, and in fact, at various times, I can take the same bit and treat it differently. And in languages like C and C++, you can run into some interesting things, right? I mean, for example, I can say, I can write a, I can write this. Now in memory, it would be stored as the ASCII code for A, ASCII code for B, ASCII code for C, and 0. Right, the null character. But I can, so S is the string. And so somewhere in memory, it's stored like this, right? If I look at memory in terms of bytes. And let's say this memory location has some particular address, let's say A. Okay, so I can say, I can force the computer to think of these 4 bytes as an integer. So what I can do is I can say int, well, so those of you everyone knows what, like I'm sure you have done C. So this stands for pointer, and S means that S is a string. So it's pointing to an array of characters, which is A, B, C, D. But I can also say int star X is equal to the same thing as address of S. In which case, I'm forcing, probably have sort of syntax mixed up a little bit, but I can force X to be interpreted as if it's an address pointing to an integer. So I can force elsewhere in my program to take the same bits and just reinterpret them as integer according to whatever scheme C uses. So the point I'm just wanting to emphasize is bits are just bits, okay? And different times you can refer to those bits in many different ways. Okay, so why does it matter to us? Okay, so firstly, we'll see that with the same 32-bit that computers are very adept at manipulating, we basically use them for a variety of data types. And in your software programs, you see them, right? I mean, we can use unsigned in, signed in, floating, all these kind of things. And it's basically the same things. Okay, so now let's start with the binary. So let's say one of the very first tasks is that, I mean, we as users like to deal with decimal numbers, right? That's what so most human user interfaces, we write numbers in decimal, and then the very first thing will somehow need to happen is to convert what we write in decimal numbers into binary. And let's say for now we are sticking with positive integers or whatever, natural numbers, so 0, 1, 2, 3 onwards. So one of the tasks we have to worry about is converting into base 2, right? I mean, in spreadsheet, let's say I may write this number 17 in base 10. But deep down, it has to be converted into a binary representation. And guess what? It has to be done by some digital logic, right? I mean, everything is digital logic. So when we write 17 in the spreadsheet, then 17 is a string, right? So somewhere the character corresponding to 1 is being stored, and somewhere character corresponding to 7. I mentioned a short while ago ASCII code, right? So ASCII stands for American Standard Character Encoding, blah, 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 something like that, okay? But if you look at the ASCII code table, it basically maps common characters that we encounter, like the one on your keyboard, into 8 bits. And sort of the tables that you can look at, for example, which kind of give that. So in 8 bits, I can represent 256 different characters. Our English language has 26 uppercase, 26 lowercase. Then I have 10 digits and a whole bunch of symbols, and also kind of you can comfortably fit in that 8-bit number. But of course, the world has many, many other languages, so you need actually more characters. So the the more elaborate mechanism then becomes a coding format called Unicode, which allows encoding other characters, even in languages where, like Chinese, for example, which has tons of characters, right? So you can represent this stuff also. So our starting point typically is going to be some string where these things are stored. And we, at some stage, then we represent, let's translate this thing into decimal digits, right? Because that's all I have. I know that the user typed 1 and 7, the decimal digits, which basically, so first thing will come to mind is, hey, how do I represent decimal digit? Maybe, so I will need 4 bits for each digit because I have 10 digits. So maybe I can represent each decimal digit in terms of 4 bits, and maybe those could be our standard binary numbers, and then I'll have some wastage. So let's say now I have 1 and 7 represented. Now I need to translate that into the integer written in base 2, because I could build computers where all the numbers were represented in terms of decimal digits, right? I could do it. I could say that, we are humans, we want to stick with that. So every 4-bit, we are going to store a decimal digit, but then we are leaving, we are only using 10 out of 16. So our efficiency would be 10 over 16, which is like not that great. So if you want to pack maximum amount of information, you would say, hey, let's take the trouble and convert these decimal digits into base 2 number so that we can fully pack. So how will we do that? So can anyone suggest to me a strategy where I give you the number 17, the decimal number, base 10 numbers 17, and say, give me a corresponding, give me a strategy so that I have a string of zeros and ones, whatever, vector of zeros and ones, which is a base 2 number using this coding, right? Power of 2 coding, which will have exactly the same numeric value, right? Numeric value 1. So how would you proceed?
You keep on dividing by 2 until you get a remainder of 0.
Right. So when I start, so great. So when I start, first time I divide by 2, I get a remainder of 1 and I get 8, right? So that 1 is basically telling me about the least significant bit, right? And then I'm going to repeat the same thing with 8 and we'll keep doing it. So the strategy is this: 17 divided by 2, 8, remainder 1, 8 divided by 2, 4, remainder 0, 2, remainder 0, 1, remainder 0, and finally 0, remainder 1, okay? And that's when I get our number 10001 from MSB to LSB, okay? So that strategy works. So 17 on base 10 is, so 1, 7, and the symbols 1, 7 in base 10 represent the number 17, and the symbols 10001 in base 2 also represent the number 17 using the coding that we described, which is the place value coding. So one question is, let's say I give you 2-digit decimal number, okay? So in this particular case, this is the digit 1 and this is digit 0, right? And because there are 10 possible digits, so I need 4 bits. So digit 0 is encoded in 4 bits, and digit 1 is also encoded in 4 bits. So I have a total of 8 bits of information, right? But how many numbers can I represent in these 8 bits using the coding I have?
Two to the power of 8, right?
No. Remember, I am coding that 4 bits correspond to the decimal digit. So
Is
each
it
group,
16? Or yes.
no, not 16, 100, right? I mean, I can represent 10 digits here and 10 digits here, right? That's, I'm not using, I'm using the 4 bits to represent 10 digits. So I have 10 valid possibilities here and 10 valid possibilities here. So I'm representing 100, right? I mean, it's a 2-digit number, right? Two digit and base 10. So 100 possibilities, 0, 0 to 99. Right, so it's not 16, it's not 256. Sorry, it's not 16 square. It's not 16 square. It is because So in each one of these digits, the numbers which correspond to 1011, 1100, 1101, and 1. What did I do? 101, 1110, and 1111, which is basically 11, 12, 13, 14, and 15, right? Or whatever, B, C, D, E, and F in hex. They are not valid, right? Not valid in our code because we are using 4 digits to represent base 10 numbers. So 100 possibilities.
Professor,
Mhm.
when we include 10 as well, because we represent number from 0 to 9.
Right. So that's why we have 10. 0 to 9 is 10 values.
No, like when you say the one not recorded in the, when you list down 11, 12, 13, 14, 15, when you include.
Oh, I'm sorry. Yeah, you're right. 101, absolutely. Sorry. Yeah. Absolutely. Thank you. Yeah. Okay. So these are invalid. And so I have 10 valid possibilities and 6 invalid possibilities. Six things which are invalid. Okay. So I basically I'm taking 2-digit numbers, and then you have to design logic which take that to bin. So you can approach this problem essentially. I mean, our output is 8 bits. 8 bits are sufficient, right? Because our numbers go up to, 7 bits are sufficient because our numbers go up to 100 only. And so 7 bits can represent 128, up to 128. So I can go through it. So essentially what you have is really 7 functions, right? Corresponding to each one of the bit, and then you design this. I'll leave it up to you how to do it, but we have seen these kind of problems before. Okay. Now, the thing is, writing everything in bits and describing everything in bits becomes quite problematic because there are lots and lots of bits in the sizes of numbers we deal with, right? On your computers nowadays, how many bits are there in are natively supported by our computers currently? Common, like if you were to buy a Mac or a PC today, what's the basic bit size of things that it operates on?
64.
64, yeah, 64. So 64, writing down 64 bits would be quite painful, right? I mean, it's a pretty large number. And maybe a decade or so ago, it used to be like 32 bits, and even that was a pretty large number, okay? So it's been very common that we group bits, and you can, so that I can, now we have to group bits, and therefore it will be power of 2. And so usually 16 gets used for a bit because I can basically add a few letters and then form a hexadecimal symbol, right? So the 4 bits, 4 groups of groups of 4 bits correspond to hexadecimal digit. Okay, so like for example, 1963 in base 10 is written as 0111, 1010, 1011, and then we group it into these groups of 4 and write it as 7AB. Okay, so the idea is that I can, this way I can kind of deal with something which is more compact to write in our human communications. But remember, deep down, computer is still only has bits. That's a fundamental operation. It's just that a group is something we interpret as, in this case, 1011 as B and 1010 as A, and so on and so forth. So you will see in documentation, stuff like that, we write hexadecimal, but it's not as if there is a wire in which we can have 16 possible values. If we are going to have, each wire only has values 0 and 1. So we will, when we write 7AB like this, that implies that I'm dealing with 12 bits, okay, groups of 4. So again, just remember how we interpret. So in this case, we often interpret bits in terms of groups of 4. Sometimes groups of 3. Octal also occasionally you will see, but groups of 4 is probably the most common one. So whatever, size 1, which is just bits, groups of 3, which is octal. So 1 is just binary, 8 is octal, and 16 is hexadecimal. You could go larger also. I mean, you can, I mean, we have used 6 out of 6 letters out of an alphabet of 26. So we have 20 remaining. So I can, although I can even go whatever base 32, right? I mean, I can write G, H, I, J, and so on and so forth as well. So you could arbitrarily extend kind of the base as well. You can think in base 32 or base 64. Base 64 is actually also used in some systems. Okay, but for us, this is going to be it. Yeah, please go ahead.
Mind explaining how you converted that number to time?
Oh, how did I convert 1963 into this thing? Using the algorithm that we had here. Same thing. You can just try it out, right? So keep dividing by 2 and you'll end up with that. Okay. Or alternatively, you can just write in Google 1963 in binary or base 2 and it will tell you. Okay. So this if I think in terms of this thing as 7AB, then essentially is base 16. So the place values are now powers of 16, and obviously I screwed up out here. This is 16 to the power 0. So it becomes 7 times 16 squared plus A times 16 1 and B times 16 to the power 0. And the numeric value of A is 10. The numeric value of B is 11. Okay, so you multiply it out and you will see that you end up with 1963.
Professor?
Mm-hmm.
In the previous slide, so you used all 12 bits to represent 1963 in the decimal system, right?
Mm-hmm.
So if we in the hexadecimal system. So even in this case, you only really need 11 bits, right? Because the last one is 0. So we only add the 0 at the end so that we can represent in hexadecimal?
Well, because we are representing hexadecimal, right? So hexadecimal is defined as group of 4. So if I give you a binary string with, let's say, 22 bits, then you are going to say, hey, if I'm going to do hexadecimal, I have to add 2 more bits to it, and we'll add 0 0 in case it's a positive binary number. We'll see later how we do things for negative numbers. Okay, so we have to extend it to a multiple of 4.
Okay, is there a way to convert from binary to hexadecimal that's like intuitive as well?
Binary to hexadecimal is just grouping, right? I mean, I give you a binary
number,
okay. Just start, right? Just group by 4. So that's just that's pretty direct.
Yeah, it's pretty direct. Yeah. So what I'm asking is, like, in binary, like, you only need the 11 of the 12 bits, right? Like the first 0 for representing 7.
Correct.
That's only there so we can represent hexadecimal.
Right. In this case, yes. Although I don't know, like, I mean, if I'm looking at 4-digit years, I don't know whether 9999 in base 10, which is the max I can do, whether that will require a 1 there or not. Okay. So it's possible that I might still need it.
Okay. Thank you.
Okay. So now let's first talk about how to do arithmetic, sticking with these positive integers. So we're not going to look at negative for now. Okay. So we have seen now I can represent positive integers 3 different ways, right? Like 2 of which are just interpretations, right? So I can think of them as a vector of bits. I can think of them as the same vector of bits, but in groups of 4, which is hexadecimal. So it's really the same as binary, so nothing really changes. And then I can write things in decimal things where in groups of 4, I represent 10 digits and I leave some of them undefined. Okay, so that's called binary coded decimal. Actually, just let me write it down also so that where did I have? Here. This way of coding is called BCD, or binary coded decimal. And in early days, if you go back to like the history of computing, there were some early computers where BCD was used. Okay, but the problem you can see is, right, I mean, anytime I'm storing things, then 6 out of 16 are not being used. So a pretty hefty chunk of memory is being wasted. So BCD kind of fell out of fashion pretty rapidly. Okay, it's really just of historical interest. Okay, so we are going to stick with binary, right? Because hexadecimal is nothing but another way of looking at the binary. So binary addition, right? So we know that again, the analogy is our base 10 type addition that we do carry out from every bit position. So just like we know what the addition of digits look like, likewise we can talk about addition of bits. So 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1 is the number with value 3, so I need 2 bits. Number with value 2, so I need 2 bits, so it becomes 1, 0. So in this case, this little one, again by analogy with our elementary school arithmetic, is the carry out. So let's say I'm doing 5 plus 7. So 5 plus 7 is 101 and 111. So what will happen? I'm going to start with LSB. So I'm going to add 1 plus 10 with a carry of 1. So the next one, I'm going to add 3 of these. 1 plus 0 plus 1, that gives me 0, and then out of 1, so carry out is 1. And then 1 plus 1 plus 1, anyone cares to tell me what would I have? Right, so here I added these, right, to get a 0 and a carry out of 1. And you can see, right, 1 plus 0 plus 1 is 2, so it's 0 plus 1 in the 2's position. Here I have to add this.
1, 1.
1, 1. Excellent. Right, so that's what I will get, and that's obviously 12. So that's what follows. So conceptually straightforward. It's exactly kind of just analogical to what we learned in text 10, right? So that's exactly that. So now the question is, how many, let's say I ask you to add 2 n-bit numbers. How many bits do I need for the sum?
N plus 1.
N plus 1, right? Because it could be a carry out, right? Not always, but carry out. So if I add 2 n-bit numbers and I only give you n-bit for the output result, that means there would be settings under which your number will overflow, right? That is, your sum is too large to represent in the n-bit. So that's what happens in software, right? I can write 2 numbers, and like I can say let's say I write this thing, right? Let's say I say unsigned, so that is positive, unsigned int x, y, z, and then I say, and then I sort of assign something, x equal to something, y equal to something, and then I say z equal to x plus y. Now, of course, x, y, and z are referring to similar sized vectors in the memory, locations in memory. So it's possible, depending upon what x and y are, z might no longer be representable, right? It may not fit into 32 bits, but I only have 32 bits. So all that will happen is that the carry out gets ignored, and then you are left with something which you might think is the right answer, but it's not. So this is called overflow can happen if I stick with constant. On the other hand, you could also imagine that I add 2 bit numbers, and you say, hey, but I need n plus 1 bits, I give you additional bit. But that's not how processors work. If you are making your own chip, you can keep adding bits to your representation, but processors are designed to work on fixed size chunks. So when you add, overflow can happen. And that's kind of something which, if you're doing binary arithmetic inside processors at a low level, you'll have to kind of keep track of. Okay, so what will happen when we add an m-bit number to an n-bit number? How many bits could I get in general there? So instead of 2 n-bit numbers, now I'm adding 1 m-bit number and 1 n-bit number. So how many bits would the sum need in general?
Would it be the max of the m or n?
This?
Plus 1, right?
But what if
Plus
they were the same?
Yeah, plus 1. right? So there can be a carry out, right? Worst case, m and n can be the same, in which case max is either one of them, and then I need one more. Okay, and in this other one, I needed n plus 1. Okay. Okay, so now let's see how we can do this addition in digital logic. So what's happening is so firstly we can see bit position 0 is kind of different than all the other bit positions, right? In bit position 0, we only add 2 things. In other bit positions, I have to add 3 things: the carry coming in from the previous location, as well as the 2 bits that I have. So so at bit position 0, we are adding 2 bits, one from each one of the inputs. Output is essentially how many ones we have, and it could be 0 or 1 or 2. So I need 2 bits, S and C. So I can really define a truth table. I can say I have AI, BI, I0 in this case, okay. And then I need, okay. So output is, this is just intended to help us out, right? So 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, and 1 plus 1 is 2. In terms of how we represent it using the 2 bits I have, the sum at bit position 0 and the carry we are feeding into the next one. So we are going to use a notation that SI means sum at bit position 0, CI plus 1 means carry going into I plus 1 at bit position. So as you can see, 0 plus 0 will have sum of 0, carry of 0. The other 2 will have sum of 1, carry of 0, and finally 1 plus 1 will result in carry of 1 and sum of 0. Looking at this, can you tell me the Boolean expression? How would you implement these 2? So let's start with this. Carry out.
It would be N gate.
It's N, right? So this AI and BI. What about SI?
XOR.
XOR. Excellent. You guys got it. So, okay. Now, of course, we can optimize it and all, but at least we have some initial expressions out here. So this thing is called a half adder. It's called a half adder because it's only, it doesn't have to deal with carry coming in. Okay. So this is what it looks like. You have a half adder, and we just saw what the logic would be. So that's a half adder. It's kind of a building block that we have. Okay. And actually, those of you who are in the honors section, we saw this little Verilog code. If you recall, those of you who are not in there, don't bother. It's how things get written in the hardware description language. Okay. Let's move on. What about other bit positions? Now here we have 3 bits, right? So, and potentially all those 3, right? There's a carry coming in, and then I have 2 from A and B. And so I could end up with values as high as 3, which means carry out of 1 and some bit of 1. So I can again kind of do the same thing. I can write down my truth table, except that now I have 8 entries because I also have a carry in, right? This is a carry. This is a carry coming into the bit position, right? And this is the carry out. Okay, and again, you can convince yourself that makes sense. So again, this output is just to help you guide like what's really happening, what value I have, and then you can see that these 2 bits here, if you think of them as a binary number, then they kind of correspond to the output value that we want, right? So again, this is a truth table. You can implement this using methods that we have learned. This is a function where there are 2 output bits, so there are really 2 functions. So you can do it. It's called full adder. Now, staring at this, things are a little bit trickier at this point, but can you again see under what condition is sum 1? So ignore carry out for a moment. Under what conditions is the sum 1?
When only one of the inputs is 1.
Okay. So
or all 3 are 1.
Or all 3 are 1, right? So another way of saying is odd number of ones are 1. Odd number of bits are 1. So this is 1 if an odd number of bits across those 3 are 1. And do you recall what this thing is called?
That's a 3-input XOR.
Yeah, it's a 3-input XOR. Okay. So the sum
Isn't
is
the
nothing
last
but,
half of the table in XNOR though?
say it again?
Isn't the last half of the table, like if you look at the last 4 lines, isn't that in XNOR?
The last half of the table. Yeah, but you can't look at just the last half of the table, right? I mean, so XOR is defined as a gate which outputs a 1 if an odd number of inputs are 1.
Oh, okay, yeah, that's right.
Yeah. Yeah.
So it works for more than 2 inputs as well, like that.
Yeah. Okay. So that's the sum. What about carry out? The Ci plus 1. So I think the pattern there is either 2 R1s or 3 R1s. Right? So
Isn't that the majority function?
yeah, it's a majority function. Exactly. Got it. So that's what it looks like. I have a majority function and I have the 3 input XOR gate. That's my full adder. Okay, so I can optimize this stuff also. So the majority circuit, this is from a previous module, is basically this function. So we had seen this thing before. And then I can, and the 3 input XOR gate, you can actually do XOR of XOR. So that works out well. Okay, so I can do that. But there is another way of looking at it. I can think of it as that I'm going to, remember, if I give you 3 numbers to add, what do? You add 2 of them, and then you add the third one, right? So I could do this, which is shown out here. I can take 2 half adders, and then sort of put them in the series, and then have an OR gate. So the reason it works is the following: that what will the half adder do? So think about it. So A and B, if A and B are both 1, then it will have a carry out of 1, right? If on the other hand, A and B are both 0, then I have carry out of 0 and sum is also 0. And if one of A is 0 and the other is 1, then the sum is 1 and carry out is 0. Now, if the sum is 1, and if I'm going to add it to the carry in, then it's another way of saying is that that if carry in coming in were to be 1, then I have to move it forward. So whereas if I have, right, I mean, I have these possibilities. I have a possibility that this is 0, this is 0. Another possibility is this is 1, this is 0. And a third possibility is this is 0, this is 1, right? Because for a half adder, I don't have the possibility of 1 and 1. So
Professor?
one way of, yeah.
Do you mind going back to the last slide? And why does the majority, or the one before that? Oh, never mind. Okay. I thought the majority didn't have the CN.
Oh, no, it does. Yeah. Okay. So, yeah. So there are 3 possibilities for this half adder, right? So in one case, it can generate a carry, right? And so that's why we call this thing G for generate. And another case, it can have some bit as 1, which basically says that if carry in is also 1, then I'm going to get a carry out from here. Right? So I can have carry out under 2 circumstances. One circumstance is that I got a 1 out here. There is a carry out, irrespective of what carry in is. And the other is that I have a sum, one of them was 1, and if carry in is also 1, then I want a carry out of 1 out of that sum of 3 bits. And that's the job that this half adder will do, right? If both are 1, then I will going to get a carry of 1. If so, right? So the half adder, you will see, will produce this. So essentially, this circuit basically says, if I get a carry either from summation of this or as a result of these 2 bits, I have a carry out, and a sum bit comes out of this. Okay, if it is 0, if it's both are 0, or this is 0, 1 is 1, depending upon that, the sum bit will come out. So you just kind of work through this thing, but you'll see that this configuration of half adder followed by an ORing of their carry achieves exactly the same purpose. Now, this is not a very efficient way of doing things, but it works. Okay, so I can use two half adders to form a full adder, or I can do it this way. Okay, if you care about efficiency and all, you'll probably do it this way, but this is mathematically, this is equivalent. Like I said, all it is doing is kind of adding 2 bits at a time. So I'll leave it for you to kind of work through. I would suggest that you convince yourself what I'm stating out here is indeed true. Try out for different combinations of. Let's just do it. Okay, so I'm going. So let's see which row you want me to do. Let's say we try this row. Okay, 1 0 1. So A is 0, B is 1, C is 1. Half adder 0 1. What would it output? Carry of 0, sum of 1. Half adder, both bits are 1. It will output sum of 0, carry of 1. So I'm seeing an OR of 0 and 1, so I get a carry out of 1 and I get a 0. Okay. And if you look out here, that's what we have. And you can try it out. Okay. So, I mean, you can reason through it, but if you don't believe it, just try it out on any of the entries of the table and you will see. Okay, so I can make full adder and with these two kind of, at least these two different ways. But now what if I want to add a multi-bit number, right? I mean, so remember in multi-bit number, we have to do this carry out, but we already see like we can do a carry out and then we know how to take a carry in. So much like our arbiter and priority encoder, we basically kind of do something very similar. We stack these things up. So we take a whole bunch of full adders, and the idea is that we feed carry in to one of them, along with the corresponding A and B, and then take the carry out and feed it to carry in of the next one, and so on and so forth. This one you will tie to 0, or you can use a half adder here, right? I mean, on this one we can use half adder. Now we'll see later on that actually we don't actually use half adder, we use full adder, because if I tie carry into 1, I can do some creative stuff with it. Okay. For example, let's say my computer is a 32-bit computer, but I want to add 64-bit numbers. Then what I can do is I can first add the lower 32-bit, take the carry out, feed it into the carry in. The next time I add the upper 32 bits. So it's generally useful to design the hardware to be more general than what you strictly needed just for 32 bit, which is why you will see that I'm using full adder even for the LSB, even though in theory, at least for our purposes, a half adder would have worked. So just imagine that we'll use the full adder, but we'll tie the carry into 0 to do addition. So this is very much like how we do addition in decimal, right? I mean, we keep feeding the carry there. So this kind of architecture is called as ripple carry architecture because the carry is rippling through this, okay? In fact, depending upon what your numbers are, it's possible that that I will not know the value of sum or carry until kind of the whole information propagates. Like for example, let's say I were to add, let's say it was 4 digits, right? Let's say I were to add this number, right? Right. So now what will happen is 1 1 0, carry out 1 1, carry out 1 1, carry in 0 1. This guy out here, it actually depends upon what happened out here on the least significant bits. So the circuit kind of really has to wait for all of this to go through. Okay. In fact, if you were to, let's say, change the carry from 0 to 1 or something, there might be a chain effect. So because of this chain kind of thing, there's a very long path through my circuit, which is going through all the bits. That's why it's called ripple carry. Carry is kind of rippling throughout this architecture. So do you see a problem with this architecture? Like what's this, I mean, it does the math for sure, but Do you see an issue based on what I just discussed?
So for large numbers, it would be very slow.
Yeah, for large numbers, it will be really, really slow. So anytime something is proportional to n, in computer science, we call it as, well, I'm not being very rigid out here, so, but like that the delay is order n, which basically means that, in loosely speaking, that it grows no faster than, or well, it grows as proportional to n, okay? Which is bad because it's probably okay if I'm adding 4-bit or 8-bit, but if I'm trying to add large digits, then it can be problematic. In our programming languages, what's the largest integer that are natively supported currently? So we saw 64, but this, can you have larger ints?
Like, are you talking about the data type int?
Well, I mean, I'm basically asking, in your programming languages, are there any integer data types which have more than 64 bits?
You can have longs, right?
Yeah, so actually long is 128. So long is 128 bits. So you can go up to 128, right? In some stuff which is optimized for things like cryptography and all, sometimes you have to deal with like even larger 256 or 1024, but our programming languages don't support it. Okay, so this proportional to n delay is kind of painful, right? I mean, you would like to have things move faster. But before we move on to it, let's see what underpins this order of n delay, right? So if I look at what is inside the full adder, so I've kind of stacked them up out here, right? That I have things going through the chain. And remember, our culprit is a chain, right? So it is this guy. Sorry. Okay. So that's how the carry is rippling through. I really don't care about the delay out here because this can still happen, the sum, I mean. So really, it's this chain that I'm worried about. So this majority circuit is kind of the culprit. So a lot of effort has gone into optimizing these full adders, right? Because if I can reduce the delay of full adder by some fraction, it pays off in every bit, right? At every bit position, I'm going to be improved. So really got to optimize that. That's really the thing. So for example, this is a circuit which does that. Oh, by the way, so as a result, remember I also often told you, I've told you guys many times that the circuit technology has inversion as kind of the basic thing. So what happens in these adders nowadays typically is that to take advantage of that, we will have C in and then we'll have C out invert. And then again, so like, so this would be, let's say, so this is C in coming in, let's say this is C out 1, and then C out 2, and then C out 3 invert. So we alternate between positive and negative so that we avoid an extra inversion in the middle, because it's costlier to do positive logic than complementary logic. Okay, so basically what's happening is that instead of we design two types of full adder, one for odd bit positions and one for even bit positions, and then the carry values are flipped, and output of, let's say, odd bits might be the true carries, and output for even bits might be the inversion of the carry. Okay, and this way we gain some more speed. So a lot of optimization done because full adder is at the heart of so many things, right? I mean, multiplication, division, they also depend on full adders. Subtraction is done using essentially these things. So full adder optimally designed can pay off a lot. So a lot of effort, transistor level hacking goes on and all. I've just shown you one particular thing. In this case, it is not flipping, so it's still even, like C in, C out. But oftentimes you will see C in, C out bar. Okay. And on the other hand, you see that from A to B to sum, I have a long delay out here, right? I mean, I'm going through many gates from the input to sum. but we don't care about it, right? Because really our long path is the other one, okay? I mean, the sum we have leisurely time while the carry is propagating, our sum can compute and we are still okay. So effort goes into optimizing the C in to C out delay. Okay, so the question then is, can I do faster than, so let's say you have done all this full adder, you have optimized out of it. Can I do faster than order of in delay? Okay, right? So now, I mean, I'm sure you have done some programming classes and we kind of worry about like, you know, sorting a list, what's the complexity of doing it, right? We like to do things faster so that as things grow, I can do things more rapidly. Let me ask you this, okay, let's say I'm multiplying numbers, okay, and let's say I'm multiplying k digit first. How does the cost of multiplication go? So let's say I give you 2k bit number or k digit number, doesn't really matter. As I increase k, it will take me more time to do the multiplication, right? I mean, how do we do multiply, right? We do kind of multiply for every, we form the partial products and then we add them. Intuitively, how does the time taken, let's say, how many, just if you were to do it manually, let's say, how would the time taken through our partial product type strategy increase with k, the number of bits or digits?
Is
So
it k squared?
Yeah, k squared, right? So multiplication is k squared. And multiplication obviously also is a very important operation. So a lot of work has gone on in making things lower than k squared. And it turns out that you can actually do multiplication in k to the power, I think 1.2 or something like that. Like, I mean, there are all these funky strategies, and these are, I mean, what I've described is a pretty recent, like within the past 2-3 years type thing. So a lot of effort goes into optimizing arithmetic operations. Now, addition is kind of relatively simpler, as in what I'm going to describe has been around for 2-3 decades. Okay, so let's see how we can do it. So ripple carry adder requires that the carry information should be propagated through the bit by bit from LSB to MSB. So question we are going to explore is, can we do better? So let's do a thought experiment, okay? Let's say I ask you to compute a function f of x. And I tell you that x can take one of two values, 0 or 1. But f of x takes a lot of time to compute. So f of 0 takes a lot of time to compute and f of 1 takes a lot of time to compute. What can you do to minimize the latency from the instant you know x, like the user tells you, hey, the x is this, and then you can answer it. So the idea is the user will give you the x, and you have to give the user the answer, right? If x is 0,
you could pre-compute f of 0 and f of 1.
Yeah, so you compute ahead of time, you pre-compute. So now imagine our going back out here to our carry chain. If I look at any portion of this carry chain, the incoming C in into a portion of the chain is either 0 or 1, right? So I can pre-compute for both options of carry in being 0 or 1 and take advantage of that. So let's see how we will do it. Okay, so it's pre-computing F0 and F1 in advance of knowing X. So this is kind of the idea. Imagine I'm going to look at a group of bits. Okay, so I have to add like large 64-bit, 128-bit number, but I'm going to focus on some group of bits. In this case, it's a group of 4. So let's say it's bits number 60 through 63. Okay. So from the lower side of the bits, the carry in will be either 0 or 1, right? So what I'll do is, I'm at bits number 60, 61, 62, 63, let's say, and coming in are the lower bits. Let's say, so those are 59 to 0. But whatever is coming in to me is either 0 or 1. So I can perform the addition corresponding to both. So I'll use 4 full adders and compute that, and I have 2 possible candidates for carry out, and I have 2 possible sets of 4 bits for the sum. And then eventually at some point, the preceding thing will tell me what the carry in actually is. And then I can use multiplexers to select between the two, right? So if carry in coming in was 0, I'm going to select this one. If carry in coming in was 1, I'm going to select this one, and likewise for the sum. So the idea is, as you can see, I'm just pre-computing while the preceding stages are computing and kind of the carry is coming in. But when the carry comes to me, I can immediately do the carry out now, right? Because my computation of the 4 bits out here overlapped with what the preceding stages were doing. So that's the strategy. It is called carry select adder. Okay, that is, I compute both and then I select. What's the disadvantage here?
More space, more gain.
Space, right? Actually, more than twice as much space, right? I mean, I have to pay for 2 times the full adder as well as these multiplexers. But if I care about the speed, like want to run my hardware at a high speed, then we will pay this penalty. So it's kind of an area, it's an area speed trade-off. Okay, we saw it previously also, okay, for our arbiter. So very common thing that happens in our engineering design. So let's see how we build upon this idea. So one way we can say is, I'm going to just divide it into some fixed chunks. So again, I'm sticking with the example of 4 because that's what the place where I picked these diagrams from had. So let's say I'm trying to do a 16-bit addition. So I'll just divide it into 4 groups of 4. The initial group is just standard triple carry adder, but every other stage I have, I'm computing both. So what will happen in this case is that instead of the delay being proportional to 16 full adder delays, it would be proportional to 4 plus 3 mux, right? So more like 7 gate delays, right? As opposed to 16. So better than half. So I can reduce the delay from input to output. Intuitively would be kind of almost like probably somewhat more than a 50% gain. Okay, you can be more precise about what it is, but the point is that I gained a lot. But can I do better? So let's think about it. Let's say if t equal to 0, we presented A and B. Let's look at this carry out. Let's look at the carry outs here. Let's say this was computed at, so let's say we started at t equal to 0. Let's say at t equal to 4, this got ready. At what time would this be ready? The carry out here. And so this was ready at t equal to 4 because it went through 4 full adders. At what time would this guy be ready?
Would it be t equals to 8?
Why 8?
Because when it, would it actually be, I can't tell if it's 8 or 12. I'm confused because it has to loop through 4 times.
Remember, I'm looking at this point right now, right? I mean, so,
okay.
So how many full adders does it have to go through?
None, right?
Would it also be 4 or?
Yeah, it would also be 4, right? It's no different than what happened out here. It's basically adding those 4 bits and the carry out of that. What about this guy?
So when you don't have the carry select adder, would this be a higher? What would that number be then?
It would. It is a carry select adder, right? I mean, so remember, we are just looking at this guy. So if I'm going through four full adders, so it's going through 4, so it's equal to 4, just like it was equal to 4 here. It would be equal to 4 here also, right? It would be equal to 4 here also, because I'm going through only 4 bit. Likewise, I'm going through 4 bits here, so this one is also equal to 4. They're all equal to 4 because these are all independent little 4-bit triple carry. Now, this carry out gets computed at 4. It arrives to this mux. And so let's say at t equal to 5, this guy gets computed, assuming mux also has a delay of 1. Right? So at t equal to 4, both these carry inputs at the input of mux were ready. And at t equal to 4, the carry out from the preceding stage also arrived. So all of them got ready at t equal to 4. So at t equal to 5, I have the carry out here at this point. This guy, its carry in, its inputs of this mux were ready at t equal to 4, but the correct carry in didn't come until t equal to 5. So this guy will be at t equal to 6. And then likewise, these guys were ready at t equal to 4, but the carry, which is this carry which is coming in, it is coming at t equal to 6. So this one will be at t equal to 7. So do you see some suboptimality out here? I mean, for example, this mux was great. All its inputs, both the data input and the select input, came at t equal to 4. But if you look at the multiplexer out here, this guy, this multiplexer, its inputs, data inputs became ready at t equal to 4, but its select input only came at t equal to 5. So I could be smarter and I can do one more bit in this stage, right? Because why finish early? My best situation is if all the inputs to the mux are ready at the same time. There's no point for some of them to become too early. So I could actually have handled 5 bits here. And I would still get t equal to 6 here. Right? Because if I handed 5 bits, then the 2 carries out of the 2 chains, one assuming 0 and one assuming 1, would be ready at t equal to 5. And that is when my carry from the preceding stage also comes. So I can do 5 bits here and still get t equal to 6.
Professor? Could you explain what the multiplexers are doing, like how they're helping in the carry select logic? Like, are you?
Okay, what does a multiplexer do?
It selects, like, given an input, it selects a particular one of its
Exactly, right? So
output.
So depending upon whether the carry coming from the preceding stage is 0 or 1, it is either going to select the carry and the sum for the upper ripple carry or the lower ripple carry. The upper ripple carry assumed carry in was 0. The lower ripple carry assumed carry in was 1. So I'm pre-computing based on this theory that we had, right? That I compute both F0 and F1. So I'm computing for those bits 60, 61, 62, 63. I'm computing A 63 through 60 plus B 63 plus 60 for 2 cases.
Oh, it's compared to the full bit, the ripple carry where you wait for every, like, you wait for the preceding input.
Let me finish.
Okay.
C60 is 0 and C60 is 1, right? It's calculating for both the cases. So here in my example, here I'm calculating both the cases, and then once I know C in from the preceding stage, I will select that. That's what the job of a mux is, right? So when and the output here can only occur after all three are available, and likewise for the sums, right? So but sums we don't care the speed of, so we are optimizing this one, right? So once the upper ripple carry and the ripple carry is done and C in is arrived, then I can compute the C out, right? So that's what's happening at every stage. The preceding stage, when it arrives, then the multiplexer output becomes valid. So the output of this multiplexer.
Yeah, I see what you're saying. Yeah.
Okay. So now the carry out of the first 4 bits became available at t equal to 4. I'm assuming full adder has a delay of 1 and mux has a delay of 1. Okay. So I'm assuming FA and mux have delay equal to 1, just to keep arithmetic simple. Okay, so this guy became ready at t equal to 4. Or both the carry chains here became ready at t equal to 4, and therefore an input of select input of mux came at t equal to 4. So this one becomes ready at t equal to 5. But here in the third stage, this stage, I have a suboptimality. 2 inputs of the mux are ready at t equal to 4, but its select input does not come until t equal to 5. So I could have done one more bit out here. And still my output would be ready at t equal to 6. So just to make sure we understand, how many more bits could I have done in this stage? So its select input comes at 6.
6 total bits.
6 total bits here, right? So I could have done 4 here, 5 here, 6 here, right? 4. So I can keep increasing the size so that, of course, and the advantage is I'll need fewer of these stages. So that's would be a smarter strategy of doing CSA, and that indeed is what you are going to see here. Okay, so here what we do is we do 2 bits here and 2 bits here, but then I say do 3 here, 4 here, 5 here. Okay, so I kind of do this telescoping increase there.
Professor?
And if you do, yeah, go ahead, please.
So earlier when you were saying that t starts from 0, then goes to 4, 5, and 6, does t refer to the number of bits?
Time.
Time?
Time. Delay.
Could
We're talking about delay, right?
Okay. Could you go over how it goes from 0 to 4 to 5 and 6 really quickly again?
Okay, so let's say the whole system, at t equal to 0, we got the inputs, right? A and B and C in all came at t equal to 0. This C in and all the A's and B's. So this thing will take a delay of 4. So I will appear at t equal to 4. Right? And likewise, both of these points also will appear at t equal to 4. And likewise, these 2 points will also become ready at t equal to 4. And likewise, these points will also become ready at t equal to 4, because all of them are going through basically full 4 adders, right? I mean, like this, right? So so let's call this thing mux 1, mux 2, mux 3. Mux 1, the mux 2 and mux 3, all of them, the 2 data inputs, which I'm going to select between, are ready at t equal to 4. But what about the select input? Well, the select input of mux 1 is the carry in coming from the preceding stage. So that is available at 4. But then if mux also has a delay of 1, then output becomes ready at t equal to 5. So for mux 2, the select input is only coming at t equal to 5. So its output will not really be valid until t equal to 6. And then for mux 3, the select input is coming at t equal to 6. So the final carry out will only be valid at t equal to 7. And the issue is that for mux 2 and mux 3, the data inputs are ready before the control and the select input arrives. So what that means is I could have done one more bit in mux in here. So I could have done one more bit here in this one more bit. And for this one, I could have done 2 more bits and still not be impacted, right? I would still get my carry at 7, at t equal to 7. So it's kind of like, let's say you and I are both doing tasks which have to come together. If I do it faster, then I have to wait for you to finish. Right? So when we are working in a team, your optimal situation is that everyone works such that we finish at the same time so that then we can put the part together. There's no point in some members of the team to race ahead while the other one is delayed. Okay, so there's a question.
Yeah. So when you say like at the bottom it says carry select adder with blocks of uniform size of 4. So do they have to be like uniform size, and do they have to be size of powers of 2?
Oh, do they have to be does the uniform size have to be power of 4? No, it could be anything.
Okay. Yeah. Okay.
Yeah. Why do you think it would be power of 4 or power of 2?
Well, for bits, usually that's like the
don't go by what the usual pattern is. That's not a good way of reasoning about anything, right? I mean, this thing, right? I mean, reason we see power of 2 in bit representation is because we are dealing with bits. Here we are dealing with number of adders. There's nothing power of 2 about it, right? It's just a number of adders.
I see.
Right?
So
the reason we get power of 2 in binary thing is because we are dealing with 2 choices. Here we are just dealing with, right? I mean, adders could be, I can design adders of any length, right? Like 5-bit, 7-bit, whatever, right? There's nothing binary about it. So no reason for it to be power of 2. And it so happens that the example I have is 4-bit, but there's nothing, no reason, right? Yeah.
Okay, yeah, that's what I was wondering. So generally, like, would there be like a specific method or reason behind picking a certain block size?
Whatever gives you lower delay.
Oh, okay. Okay, that's fair.
Whatever this number is your final thing, right? You want a fast adder, right? That's really what we care about. Now, what we are seeing already out here is that we are entering into the situation where in parts of our circuit, some inputs are coming sooner than the other inputs, which is wasteful, right? Because the inputs which came sooner are having to wait. So a good hardware design, or actually for that matter, a good software design, is one where all the inputs are ready at the same time. So that motivates kind of this structure where what we do is we first in stage 1, the first 2 stages, I do 2 bits, two full adders, okay? And then for the next one, because I also have stage 1 mux to hide, so I can do 3 bits. Next one 4 bits, next one 5 bits by the same logic we saw. So what will happen now is that at what time would this guy be ready? T equal to
2.
T equal to 2. Good. And then these guys are also ready at T equal to 2. So the output here would be T equal to 3. And what about these guys? Well, they're changed.
Professor, I'm a little bit confused. Can you be a little bit more specific when you say these guys are ready at certain times? It's just a little bit hard to tell what's getting ready at which time.
Sure. So by these guys, so actually you should see where I am coloring at the time when I say, okay. So this point where I'm squiggling right now, do you see it?
Yes.
Okay, that's T equal to 2 because coming through 2 FAs. Let's look at this point, the one where I'm squiggling now. That would also be T equal to 2 because it's going through 2 FAs. Likewise, the output of these 2 FAs will also be T equal to 2. So when seen from the perspective of this first stage multiplexer, all its inputs are getting ready simultaneously at T equal to 2. Therefore, the output of first stage multiplexer, which is this line, would be ready at T equal to 3. Likewise, the output of these 2 chains of 3 FAs, they will be ready at T equal to 3 because they are going through 3 full adders. So again, this multiplexer at stage 3 will get all its inputs at T equal to 3. So that's what we want. And therefore its output, which is this guy, okay, output of stage 3 mux is T equal to 4. And same thing will hold true at the next stage. So at this stage, the select input is t equal to 4, and the two data inputs are also t equal to 4, because they are going through 4 full adders. So everything is optimally balanced now, right? Output of this stage 4 multiplexer will be ready at t equal to 5. So when we reach this final stage, this is at t equal to 5, and the two inputs to the mux, which are coming from chains of 5 long, would also be t equal to 5. And therefore, the output would be t equal to 6. Yeah. So if I had done all of this using a single ripple carry, that was 16, right? Full adder delays. But now I have ordered a delay of 6, much faster. In general, if you follow these strategies and do it smartly, your delay can grow only a square root of n, which is a big win, right? I mean, if you plot order of n versus square root of n, then square root of n grows much more slowly, right? For a 128-bit, 64-bit adder, let's say the delay of adders are 1, then a 64-bit adder would have a delay of 64 done ripple carry way, whereas done this way, you would be able to get away with 8, okay, and so on and so forth, right? So it can really give advantage at higher things, but at the cost of more area, okay? So because I'm using twice the number of full adders and I'm using those multiplexers. So we gain a lot, but at a pretty significant cost. Area, also power will go up because I'm doing twice the computation, right? Anytime you pre-compute, right? I mean, we are paying the penalty of more computation, more work done. But this is one way of doing faster addition, right? Carry select add. But that's not the only way. We can do even faster and at even more cost. So again, this has been an area where people have tried to optimize things a lot. How fast do modern processors run? Anyone? Like if you buy a laptop today or whatever PC today, how fast? What's the frequency at which the Intel processors in it run?
3 to 4, sometimes 5 years.
Yeah, 3 to 4, sometimes 5 gigahertz. Okay, so which means that so how much? What is a time period for 5 gigahertz? Like what's the clock period? Like if I have a clock running at 5 gigahertz, so what is the period of one clock cycle? Anyone? What's the period of 1 gigahertz? What's the period for a 1?
For 5 gigahertz, it's 2 to 10 times 10 to the negative 10th.
Yeah, well, okay. It's going to be 1/5 of a nanosecond or 200 picosecond. And we do 128-bit addition and probably some other work. So your additions are going to be in few tenths of picoseconds for those 128-bit numbers, like that, right? I mean, we have very little time to do. So as you can imagine, and not just addition, I mean, we do entire multiplications, and we talked earlier that how multiplications have order n square, right? Additions being done. So there's a lot of work on making these things super fast. Okay, so you kind of try to make full adder fast, and then you play all these architecture games. So I'm going to show you one more strategy, which is probably the most powerful one. Okay, so it's called carry look ahead adder, and this is a little bit this is conceptually harder, but it's the more powerful of the strategy. So the basic idea is the following: that at each bit location, instead of deciding what the sum and the carry are, we are going to compute two things. We are going to say, is this bit location generating a carry? By that I mean that the carry out will be 1, irrespective of what the carry in was. And the other case that we will worry about is that will this bit position propagate the carry if 1 comes in from the right? right? So if I'm looking at a multi-bit number, right, I mean, let's say I'm adding two A's and B's. Okay, this is the A and this is the B, and let's say I have a whole bunch of bits, n bits, and I'm just focusing on, sorry, I'm just focusing on one bit out here. Okay, let's say bit number 60. One bit. So there are two possibilities. There are two things I'm going to worry about. Firstly, just looking at these bits, A and B, will they generate a carry? Right? That is the carry out from this bit position, will it be 1? And that would be true if both A and B in that bit position are 1, right? Then I'm generating a carry. And the other situation is that I'm propagating a carry, which is if a carry comes in from bit number 59, then I'm going to just pass it on. So imagine that I have created these two signals. Okay, one we will call it generate. Am I generating a carry? And the other is whether I'm propagating a carry. Okay, and you can see in this table, 1 1 1 1 means I'm generating. Other scenarios correspond to propagate, right? For example, if A was 0, B was 1, and C in was 1, then C out will be 1. So that means I'm propagating. There are a couple of slightly different definitions of propagate that people use, but we are using one of them. If you kind of work out the truth table for this, then propagate means A or B, or in some cases AX or B. And generate is A and B. So let's see. Look at this equation. It's saying carry out is high if I generated a carry, or carry coming in was high and I propagated, right? So I'm saying carry out if one of these two are true, or both. I generate carry. Number 2, I propagate carry, and carry in was 1, right? These are intuitively the two settings. That carry out from my bit position would be high if I generated a carry, which means both my bits were 1, or carry in was 1 and I'm propagating it. So which means, right? So those are kind of the situations under which this will happen. So that results in a circuit where, imagine that I'm generating this. I'm saying at every bit position, I'm going to compute generate and I'm going to compute propagate. Okay, and from this propagate and generate, I can always, and given the carry in, I can compute the carry out. So we are going to stop worrying about sums at this point, because again, our culprit is the carry chain. And let's see how we can make use of this. So the idea in carry look ahead adder is the following. Again, going to look at groups, and again, doesn't have to be groups of 4, although there will be some advantages in powers of 2 here. So let's consider this group of 4. Okay. So what's happening is that each one of these full adders, now they are outputting this propagate and carry that you see out here. Okay, they're not okay. In addition, they're outputting the sum, and they take a carry, right? So this is a kind of a modified full adder. I'm not computing carry out here. I'm computing carry in. I'm computing sum, and I'm computing propagate and generate. And for each one of these 4-bit positions, 0, 1, 2, 3, I'm going to do the same thing. Each bit position is telling me, will it generate, will it propagate, will it generate, will it propagate. And kind of the idea is that out of this group of 4, I can then say whether this group as a whole is going to generate or propagate. Okay, that is, are the values within this group of 4 such that we know for sure that the output C4 will be 1, that is, it's generating a carry. And likewise, PG says, so this is group generate and this one is group propagate. And this purple thing is called as look ahead unit. The idea is P and G, the propagate and generate signals which I'm getting, have sufficient information for us to immediately decide that whether I'm generating a carry, and so I can immediately say what is C4, or will I propagate the carry if one were to come in from the right. So this becomes a building block. And then what happens is we are, and you can write down the equations for this, right? So I can, on the previous slide, we had seen what the equation for carry look like, C1, C2, C3, C4, which was in terms of G, P, and C. But I'm going to flatten them out. I'm going to do a two-level implementation, sum of products, for example. And that's what you see out here. So I convert them into two-level. See, the problem with the equations out here is C1 depends on C0, C2 depends on C1, C3 depends on C2, C4 depends on C3. So therefore, C4 has to wait for C0. That's a long chain. But I can take all these equations and then flatten them out. So see how C2 now is in terms of C0 only. C3, I rewrite it so that it's in terms of C0. So I keep plugging in, and C4 is only in terms of C0. Okay. So I rewrite these equations so that I can compute C4 immediately in terms of in one go. So as soon as C0 arrives, C4 can be done within one gate. Whereas previously with ripple carry, it would have gone through 4 gates. So that's the advantage of this look ahead unit, that I am pre-computing propagate and generate, and then flattening out this circuit. This is kind of a fast circuit. And that allows me to, as soon as C0 comes in, within 1 gate delay, C4 will be ready, as opposed to 4 gate delays. And if I had picked some different number, let's say 8, then again, so very rapidly, because I'm using this complex gate out here, it is sum of products, but 1 gate delay, I'll get through. And then what we do is we stitch these things together. We kind of form a tree. So we take a carry look, that group that I just showed previously, and then I take another carry look ahead unit and combine this group of 4. And if I want to make a larger adder, I can do another one. So it kind of looks like a tree structure now, where 4 adders feed into a carry look ahead unit, then group of 4 groups of 4 feed into another look ahead unit, and I can repeat this process this way. This is kind of a trickier adder to understand, but what happens now is that I'm forming a tree, right? I mean, 4 groups of 4 here are feeding into a look ahead unit of size 4, right? And then the same thing could be done with another groups of 4. So it's kind of a tree type structure which will go down. And if you think about it, a tree has a depth of what? Like if I form a binary tree, for example, okay, with where sort of at every place I have branch of 2, then the height of the tree or the depth of the tree is logarithmic with the number of leaves we have. So what happens with this kind of delay is that the delay goes as log n. And for and you can make things like, for example, a 16-bit carry look ahead adder takes 8 gate delays, and versus a ripple carry takes 47 in some example I saw. Main point is log n is even better than square root n, right? If you sort of, as the numbers go larger, the gains become even more. So if you're trying to add, let's say, 2 256-bit number or 2000-bit numbers, then carry look ahead error really will shine, because log n would be a lot less than square root n. So this is probably the most advanced type of adder that is used commonly. There are several variants of it, but kind of the basic strategy remains that now we are organizing things in a tree-like structure.
Professor?
Mm-hmm.
I get like how you calculate each 4-bit carry look ahead adder, like the blue section, but then what's going on in the purple section? Can you explain that again?
Okay, so so in the purple section we are calculating C4. Okay, so the C4 that we are calculating is now this new equation, which is obtained basically by in the blue equation for C4, I plug in the equation for C3. So now I will have an equation in terms of C2. Then I will plug in the value of C2. So I kind of resubstitute until I have an expression of C4 only in terms of C0. And of course the P's and G's. So the idea is that as soon as C0 comes in, I can immediately calculate C4.
So
Without having to ripple through. Okay, so these red equations are basically obtained by resubstituting things, right? So I take the value of C1, plug it into the equation for C2. So now C2 is in terms of C0. Then I take that, plug it into equation for C3. So then C3 becomes in terms
What's
of
the
C0.
P and the G again? Is that propagate and generate?
Yeah, G is generate, P is propagate. G says I'm generating a carry irrespective of what carry in would be. And propagate says, hey, I'm going to propagate a carry, right? If the carry comes in. So
That's going, so it's going like each bit at a time. So it's like, if a certain bit, A0 and B0, or like 1, 0, it's going to say that I'm...
These P0, G0, P1, G1, P2, G2, P3, G3 are computed in parallel, right? Because if you notice, each one of the 1-bit full adder is independent, right? As soon as it sees as soon as it sees A and B, it can generate P and G, right? So P and G can be generated very rapidly. If you go back to the equations for P and G, they're only in terms of A and B, right?
Mm-hmm.
Okay, so in this blue things, the P and G outputs can be computed very quickly.
Yeah.
So the purple thing will have the P's and the G's very quickly, and then it can compute most of C4 except the part which depends upon C0. At some point, C0 will come in from the previous stage, and then it will compute C4. So C4 will compute within one short delay of C0 arriving.
Oh, okay.
Right? And then meanwhile, C1, C2, C3 will feed in, and then S1, S2, S3 will get computed, but we don't care about their delay. What about these two? We need to compute the group propagate and group gate, and that works the same way. A group will propagate if all the propagates are right. I mean, a group will propagate if bit, in this case, all the 4 bits are propagating, and a group will generate if bit 3 generates, or bit 2 generates and bit 3 propagates, or bit 1 generates, bit 1 generates and both 2 and 3 propagate, or likewise. So that would be the group generate in case we want to stack it up. And then finally you can compute carry generate is group generate or group propagate and carry in, which is actually the same as C4. The basic thing here with this generate propagate mindset is that my carry out is 1 if I am generating, and carry out is also 1 if I propagate and the carry coming into me was 1, right? These are the 2 scenarios that any set of bits will generate. Their values could be such that they are generating a carry, or they are propagating a carry which came in. And so we are structuring addition in terms of this generate and propagate. And generate and propagate can be computed very quickly because they don't depend upon carries at all. They are a property only of the A's and B's.
Yeah, that makes sense. Okay.
Okay. So, and then we organize the whole thing into this tree, and we end up with our delay would be proportional to the depth of the tree or height of the tree, and that is order right. So this is height of tree.
So are we assuming that C0 always starts at 0, or is it based on like what they give you in the table initially?
I'm not sure I understand your question. C0 to the, so in this case, in this 16-bit adder, C0 will be starts at t equal to 0. Starts at time t equal to 0. The tables have to do with the values. They don't have to do with the time.
Yeah, I meant like the values. So see, like the subscript 0 is just for the time at time 0, right?
No. Subscript 0 is basically saying it's a bit coming into position number 0 of the whole adder.
Okay, yeah, so that's what I was asking.
Right.
What value are we giving C0 to start out with?
For addition, we'll give it 0, but later on you'll see that the same hardware is used for subtraction also, in which case we give it a value 1. And also remember, this module can be reused to make even bigger adders, in which case a group may get carry in from a previous group, right? So just think of it as carry coming into position 0 of this group.
Got it. Okay.
Could be 0, it could be 1, depending upon how you're using it.
Okay, that makes sense.
Okay.
So usually if, like, let's just say we're not continuing from a previous addition operation, we're just adding like A and B, then it would start at 0. But then if we're adding like A and B and C, then when we get to the point where we add C, it would be whatever we left off of for A plus B, right?
Right.
Okay. All right. Thank you.
Okay. So this carry look ahead adder is it's kind of obviously more complicated than carry select, and certainly absolutely relative to carry ripple. But the gains are basically that in one case we have linear growth, in the other case we have square root, right? So how does the square root grow? So let's see. So 1, 1, 4, 4. So now it will be something like this, and it will grow. So log will grow even more slowly. Okay. So basically, this is you might want to check out like what is the fastest we can do addition, right? I mean, are there even better algorithms in log n? Now, sometimes what happens is the proportionality is not the complete story, because sometimes it may come up with so much overhead that it's not worth it. So these CLAs, these carry look ahead adders, are actually pretty costly. Okay, even more area than you would give up. And so unless you are doing like additions of like 64-bit or 128-bit or something like that, it's probably not worthwhile. For smaller adders, maybe carry select might do the job perfectly fine.
Professor?
Yeah.
Oh, could you go back to the previous slide? What's the point of the propagator and generator that are leaving the look ahead?
I'm having a hard time hearing your voice. Can you come closer to the mic, please?
Yeah. What's the purpose of the propagator and generator that are leaving the look ahead carry unit?
What is the purpose of propagate and generate?
That's leaving in the bottom right. That's leaving the look ahead carry unit.
Actually, can you write down your question onto chat so that?
Professor, in the bottom right corner of your diagram, you have capital PG, capital GG. What's the purpose of those two, I think is the question.
What's the purpose of those? Okay, because I can take this group of 16 and then use, let's say, 4 of these group of 16 tied together. So let me draw it out. Okay, so okay, so let's say we are going to call this whole thing as CLA 16. Okay, 16-bit CLA. And now let's say you come to me and say, you know, I need to make a 64-bit thing. So what I'm going to do is I'm going to use 4 CLA 16-bit. Right? And I will take their group generate and group propagate. and feed them into another purple unit. Okay, and the carry in will go here, and carry in will also go here, and then this will supply the carry in here, this will supply the carry in here. So I can form another, and then, so now this thing becomes CLA 64. And then I can take 4 of these to make CLA 256 with another look ahead unit. Okay, so that's the idea. So the reason we are creating these PG and GG is so that the next layer up can use it. If you plan to just stop here, if all you cared about was a 16-bit CLA, then you don't need the group propagate and group generate. Okay. So essentially these 2 bits here, the group 1 is playing the same role of what we were getting out of the 4-bit group.
All right, thank you so much.
Okay. Okay, so yeah, we can skip this slide. Okay, so so what we have at this point is we know how to do fast additions. Later on, we will see how we can do fast multiplication. Sorry, we can do multiplication, but you already, I mean, at least from our basic arithmetic, again, kind of elementary school stuff, we know how to do multiplication, long multiplication, right? So we could do that. Division is much harder, so we are not even going to touch here. But what we are going to do next is to do negative numbers. Okay, so thus far we had kind of assumed all the numbers were positive, right? Even our discussion of addition was like that. So much of it this we'll do next time, but I just want to sort of give you that how can we represent negative numbers, right? So remember early on today I said bits are bits. It's just how we choose to represent something we care about in it. So there are 3 common ways of representing negative integers in binary. One is called sign magnitude, one is called 1's complement, and the other is called 2's complement. And there are analog of this in every base. So like if you were talking base 10, then there is sign magnitude, there is 9's complement, and there is 10's complement. Okay. So for every base it exists. So the idea behind this thing is the following. In sign magnitude, so on what we'll do is we will set aside 1 bit to represent the sign and the rest of the bit to represent magnitude. So this is magnitude and this is sign. And 0 means positive and 1 means negative. So essentially I'm saying, hey, you want sign numbers? Great. I'm going to let you take 1 bit to represent the sign and the rest is the usual binary number, right? So if you see minus 23 is the same 1011 as out here, same. These 2 are the same, right? But 1 changes. Okay. Very nice, very intuitive. Do you see a problem?
It's a waste of memory.
It is what?
You're wasting a bit.
Well, but I do have to, no, you don't have to waste a byte, right? I mean, what I can do is I can take a byte and then take the upper bit to be the sign and then 7 bit of magnitude, right? I can do that.
Yeah,
There's
2 possible representations of 0.
Yeah, there are 2 possible representations of 0, right? So all zeros and this guy. They are both, so it's kind of like a +0 and a -0, right? So there are 2 possible things. More importantly, it kind of leads to ugly hardware. If you attempt to do addition, multiplication, stuff like that, it turns out that you have to kind of worry about, you have to kind of deal with things a little bit here. There is 1's complement. Okay, so I'm going to stop at this point, but kind of the main point, highest bit is sign, rest is magnitude. What numbers I can represent? Well, 1 bit is going into sign, so magnitude can only be n-1 bit, right? So, and the highest number I can represent in n-1 bit is in magnitude, 2 to the power n-1 minus 1. So I can go from minus that to plus that. And as one of you already noticed, I have two ways of representing 0. Okay, so that's the sign magnitude. It's not, I mean, for any rationally designed computer hardware now, you will probably not see sign magnitude. But early on, when this debate was not settled, often did. Okay, so we'll reconvene on Tuesday. Also, tomorrow's discussion section, just remember the TAs are going to cover the two things that I did not cover from the preceding module. One was the read-only memory, and the other was the way doing the magnitude comparison, but from MSB downward. So they're going to spend some time just going over that. So do make sure to either attend or watch the video for that. Okay. So any questions before I hang up?
So you said the capital PP and PG and CG that you had in the that you were going to continue it to a more than 16-bit, right?
Yeah, I mean, if I want to take this group of 16 and want to now make a 32-bit or a 64-bit kind of an adder, then I'm going to stack them up, right? So that's what I was showing out here. I can always keep doing this. So the group one, see, out of this group, it's not really any different than what was happening here, right? I mean, here I was taking 4 1-bit adders and then combining them into a group of 4. In this slide, I'm taking 4 groups of 4 and combining them to form a module of 16-bit, right? So at every group, I have a group propagate and a group generate, and whose interpretation is that does this group generate says this group generates a carry. It doesn't matter what's coming in, it generates a carry. And group propagate or propagate for the group says that this group will output a carry of 1 if a carry in were to come. And at every stage we do the same thing. So it kind of gives a modular way of designing an adder, but in this tree-like manner.
Is it usually grouped in groups of 4?
Yeah, for carry look ahead adder, you do use powers of 2, not necessarily groups of 4, but powers of 2. And the reason is because you're kind of trying to form a balanced tree. Okay, so you will see groups of 2 or 4 or 8 or and so on.
So in those cases, to like kind of go off this question, do you need uniform, or I guess that's just what you said then, for the balance tree? Okay, yeah. Never mind. Sorry.
Yeah, it's kind of sort of becomes like a obvious generalization, and you can mix and match, right? I mean, you can have, let's say I want to make a 32-bit look ahead adder, right? So I can use these 2 groups of 16, and then I can use a look ahead unit of which is designed for 2, okay, instead of 4. So I can take look ahead unit of size 2 or and then take 2 groups of 16 and then make a 32-bit look ahead adder.
So when we're talking about the speed of the adders, if we use different group sizes, would the speed just be the base of the group? Like if we have 4 groups, then it would be log base 4 of n?
No, it's still log n. Okay, so actually, eventually the base of the log doesn't really matter when you are really discussing the growth rate. So more important for purposes is the tree be balanced, right? I mean, I can always make a tree which essentially boils down to a kind of a very tall tree, right? I mean, so the idea is that your tree should be balanced. At every stage, you should fill the tree before you move to the next stage. So, and then if you do that, whether you do log base 10 or base 2 or base 16 doesn't really matter. It's just a multiplicative factor. Don't think of like log n gives you the precise delay. It just gives you how the delay changes, right? There is still a constant multiplicative term which is going to be in front of it. To do the proper delay analysis was the slide I skipped over. Okay, you really have to walk through stage by stage how the delays are happening, much like I did for carry select adder. You're not responsible for this slide, so don't worry. You basically have to sit down and look through the circuit and see how the delay is, what the length of the path is. Basically, what you do is from the carry in of the 0th bit to the carry out of whatever your final bit is, you basically see which is the longest path to my circuit, and then compute and then report that. So that's what software does for you, right? I mean, it finds the longest path.
Right, thank you.
Could you go back? Yeah, could you go back one more slide? Yeah. So basically, that one. So basically, you're saying that this carry look ahead adder works better than the carry adder, because in the select adder, then you got up to like the last one, 8, 12 to 15. You had 3 seconds for the previous 3's output of the carryover to come through, and then you could output it. But in this case, you can calculate the last guy's carry immediately once you get the first one.
Yeah, so intuitively, it's a little tricky to understand, but basically intuitively what happens is that because of the way using those red equations here and we do this PG and GG, it turns out that at any stage, the moment it gets the carry here, within 1 gate delay, it computes this immediately. Okay, so within 1 gate delay, it computes that.
Wait, so is that the last 4 bit? Like, is that the delay of? Oh, sorry, the carryover of the last 4 bits?
It will be the carry delay for every look ahead unit. So what happens now is, as you make this tree, it's imagine kind of a tree. So let's say I have these 4 groups of 4, lots of them. Right, I have a very wide adder, okay, and then I'm making a look ahead unit. I'm making another look ahead unit. I'm making another look ahead unit. Right, so these were 4 bit each. Okay, and then this look ahead unit, and then I may have another look ahead unit tying together these. What happens is that each look ahead unit only adds a delay of 1, because when it receives the input from the preceding stage, it immediately generates the output. Okay, 1 gate delay later. Even if you stack them up, their group propagate and all are immediately ready. So basically, the effect is that instead of that you are kind of racing ahead through these look ahead units. Each look ahead unit adds 1 unit delay. And likewise, at this level is 1 unit delay. So, and the reason that is happening is because we are calculating in our example the C4 through this flattened equation. So instead of paying a penalty of 4 gate delays in our example, we are paying a penalty of 1 gate delay, and which is why for the tree, what will happen is you have to go all the way to the bottom of the tree and come back up. But the number of stages you are adding is basically proportional to the height of the tree, as opposed to the number of bits you have.
So you're saying that instead of waiting,
that's what it.
So you're saying that you have to wait for 4 gates versus 1 gate when you were talking about that. Like numerically, I'm just trying to picture this. So you're saying that if you didn't have a look ahead added, then you would have to go through each bit, like 0 through 3, each one of its. And then that'll be a 4 gate delay for the first 4 bit itself, and then that delay gets propped over. As compared to in the look ahead, you don't have to do that. Is that what you're saying?
Well, I don't have to ripple like a ripple carry adder, right? I mean, so in a ripple carry adder, I have to go bit by bit by bit. Here, at the lowest level, I have the structure, right? So what is happening here is that propagate and generate got computed by each one of the 4 bits in parallel, right? I mean, if you look at the equations for propagate and generate, they do not depend upon the carry in. They only depend on A and B. So let's say in 1 gate delay or whatever, some gate delay, the propagate and generate become ready out of each one of the full adder that we have out here. And then the moment those are presented to the purple box, then the purple box can calculate the group level propagate and gate again very quickly, okay, using the equations that we have out here. Okay, again, these are flattened out. So at every stage, I'm only paying a constant amount of time at every stage of the tree. And so there is no place where I'm kind of rippling through all the adders in one go. So that's where the win is coming from, right? I mean, I'm not traversing from bit 0 to 63 in 63 step or whatever, 64 steps. I'm basically kind of going deeper into the tree and coming back up.
Oh, okay. I think I can picture that.
Yeah, I think it's kind of hard to explain. Without the easiest way to do this thing is to actually simulate the adder and then see what is happening. But this slide, which I think I copied this text from Wikipedia, it kind of shows that how the timing is going within the because if you sort of are interested, you can follow through it. But it's a complex adder, so I mean, I won't sweat too much over it. But I just wanted to give you guys a flavor that there exist these kind of advanced adders, and main thing takeaway is for your future lives, if you ever need it, which is carry look at adder is the delay grows logarithmically, and which is for large number of bits that really pays off. Okay, any other question?
Okay, I think in the diagram that you said explains it, going down and coming back up. Okay, thank you.
Okay, so there was something about 1/5,000 seconds from Ryan. What is that about? I don't understand the question.
I think it was from earlier when you were asking about like how many seconds it takes for one clock cycle for the modern processors.
Okay.
Yeah.
Well, it's obviously far off from 1/5,000, so that's fine. Okay, great. So if no other question, then I'll hang up and see you guys on Tuesday, and we'll be shipping out the homework hopefully by Sunday. Okay, so next Wednesday. Okay.
Thank
see
you.
Guys. Yeah. Bye.
Thanks, Professor.
Bye.